Uh, Hello, my name is Aristeidis Geladaris. I am a PhD candidate at the Hellenic Mediterranean University, and I am working as a robotics engineer at TWILS. Today I'm going to present our work on real-time local map generation and collision-free trajectory planning for autonomous vehicles in dynamic environments, with the contribution of Mr. Lampis Papakostas, Mr. Athanasios Mastrogeorgiou, Professor Sfakiotakis, and Professor Panagiotis Polygerinos. This presentation is organized as follows. We will start with the problem that our work focuses on, and then explain the limitation that we have encountered while working with the current system-of-the-art solutions, state-of-the-art solutions. I will mention the key points of our approach and some background information over path planning and SLAM, and then I will introduce the contribution of our work to the state-of-the-art and the tools we utilized for our integrative work. Finally, I will present our testing environment and the results of our work, and I will close my presentation with the summary and the future work. So, the basic problem our work wants to address is the navigation of autonomous vehicles in GPS-denied environments, where localization and local map creation are challenging tasks. The next step is navigating in a human-populated environment where the obstacles are moving and the environment is dynamic, thus making fast detection of potential collisions really important. Going over bibliography, we have come to the conclusion that the current state-of-the-art solutions are limited on map size and map resolution due to memory consumption. Whereas most mapping algorithms are unable to accurately identify moving obstacles, and they require a number of sensors. Additionally, path planning is strictly linked to the type of the vehicle. So, in this work, we have developed a real-time trajectory planning algorithm able to work on different robotic platforms using only a range sensor that can provide accurate localization and mapping and obstacle detection in both static and dynamic environments. The distance information acquired from this process can be then used for path replanning and for the generation of a collision-free trajectory. Now, some general information about path replanning and SLAM. Path replanning can be categorized in three different approaches according to the way the control points are determined. So these are search-based, optimization-based, and motion primitives-based approaches. SLAM algorithms discretize the 3D space with the use of voxels or a 3D mesh, and they detect occupied space. With this information, the distance from the obstacle is estimated, and the occupancy map is generated. The contribution of our method in the integration of is the integration of a state-of-the-art mapping system in a widely used optimization-based path replanning algorithm. With the combination of these methods, we can achieve fast updating of the local map of the robot with an accurate handling of dynamic environments by acquiring the distance information from an incrementally built ESDF map. Additionally, the path planning algorithm we use is modified for mobile robots, making our algorithm suitable for different types of vehicles that operate in the same environment. In this slide, we can see the EWOC algorithm, which is an optimization-based algorithm for trajectory planning. What it does is that it creates a local map of the environment, and it can give accurate results for obstacle detection and obstacle avoidance. However, it's limited in static environments as the created map cannot handle moving obstacles. Next, the FIESTA algorithm it creates an occupancy map. It's a SLAM algorithm, and it's based on an incrementally built SDF map. It can achieve high computational performance, and is also able to operate in dynamic environments because it is based in two independently updated queues for inserting and deleting obstacles. Now, in our method, an ESDF map of the environment is created, and the distance from the obstacles is estimated. And we use this information as an input in a cost function that is minimized via an optimization process like the one described in EWOC. The cost function we use is modified in a way that can restrict the solutions in the XY plane, thus giving feasible solutions for the case of mobile robots. The result is the generation of a collision-free trajectory for any type of vehicle. Here you can see the testing environment we used for the cases of static and dynamic obstacles for both a rover and the UAV drone. The static obstacles are the same for both vehicles, so the environment is the same. However, for the rover, the dynamic environment is a person that passes in front of the rover while it is on its path. And for the case of the drone, the dynamic environment is a bar that falls in front of the initial path. So in these slides, you can see some videos from our results. They're in simulation, in gazebo simulation. The pink line is the initial path given to the robot. The yellow blocks are the obstacles it detects using our mapping technique. And the blue dots are the replanned path in order to avoid obstacles in its path. We have used the distance threshold from the obstacles in order to make sure that there are no collisions during the motion of the robot. So as you can see, our robot replans its path and is able to reach its goal point without collisions. I will move on to the next video. I think you get the point. So the next video is the drone operating again in a static environment. You can see, like before, in the pink line is the initial path. The blue tiles now are the generated map of the obstacles. And the yellow and black dots are the replanned path. Again, the drone can reach its goal point without collisions, as it can avoid the obstacles. Moving on, we can see the case of the dynamic environment, where a person walks in front of the vehicle as it moves. You will see that it intersects with its path, and our algorithm can see the movement and will replan its path. So again, the yellow tile is the obstacle. In this case, it's the person. The robot sees the person, but then it replans, and it replans again in order to avoid the unnecessary maneuver that it would have in the first case. And then it reaches its destination. Now, the dynamic case for the UAV, you will see that a bar will fall in front of the drone. It will see the bar, and it will replan its path accordingly. Now, what we can achieve with our approach is what you can see in the next slide. We use a dynamic map, a dynamic local map. So, as you can see in the bottom, in the bottom rows, the dynamic map can see the movement of the obstacle and avoids unnecessary maneuvers, whereas with the use of a static local map, a wall is created in front of the robot, and it has to spend more time replanning its path, and it makes an unnecessary maneuver that there is no need to do. So you can see here the completion time and the max deviation from the initial path for both cases. I mean, with the use of a static and a dynamic map. In blue, there is the result. In blue, you can see the results of our approach, where the dynamic map is used. And you can see that both the completion time and the max deviation from the initial path are minimum in comparison with the static map. All in all, our approach has produced a modular algorithm that's ready to be deployed in any time of autonomous vehicle. It can handle dynamic environments due to a high rate updating of the local map, and it can generate a collision-free trajectory, avoiding any unnecessary maneuvers. As for future work now, a real-world implementation is necessary for performance evaluation, and we believe we can have some significant results for robot cooperation. Also, we propose some changes for deployment in an autonomous underwater vehicle, which is a more challenging task due to the nature of the vehicle. Thank you for your attention, and you can contact us for any further information. Yep, of course. Yep. We actually use a LiDAR sensor, so it's a laser. Yeah. It can give us a good range, and also we can use it for localization with some odometry algorithms. Yeah, in the simulation, yeah. It's a 360 LiDAR, so thank you.